Hey everyone, this is our senior project. It's a bio-inspired aerodynamic design. My name is Jason and my partner's name is Isaiah, and our project advisor is Dr. Carlos Castro. So our objective was to analyze aerodynamic performance of flying squirrels and wingsuits and see what we can learn from them and from the performance of the flying squirrel and how we can use that towards uh, further analyzing and implementing on wingsuits. So the first step to the process consists of the research where we examine literature of the flying squirrels. Next, we use SOLIDWORKS for simulations and analysis to run these analysis on the flying squirrels and how we can use that towards implementing wingsuits. And our last process is the application and design where we took these results from the simulations of the wingsuits and apply them to modifications of how we can improve on the wingsuit design. So here we actually have a clip of a flying squirrel to help the audience visualize how they depart, how they glide in the air as you see right now, and how they land. And this video is provided by PBS Nature. So as you can see, the squirrel for most of the flight is parallel to the ground. And with a closer look, you can also see the tail is aligned with the body as well. So as it approaches the tree, you can see the orientation is almost vertically. So a brief fluid mechanics summary, airfoils result in an unequal pressure distribution above and below an object. The increased pressure beneath corresponds to an increased velocity, and this inequality actually results in a lift force which pushes the body upward, and this can actually work in reverse as seen in spoilers, which result in reduced lift. So the flow analysis of a flying squirrel was actually taken on SOLIDWORKS, and forces and velocities in the X and Y direction were used. The area was calculated using image J, and our air density we used 1.204 with a velocity of 9 meters per second and an angle of 40 degrees. And as you can see, the scale of the flying squirrel that we used was about 30.5 centimeters.
So here we have the actual data of the lift coefficient with respect to the angle of the squirrel's body. As you can see, as the squirrel goes from a lower angle, the bottom one being -6, to a higher angle, the top one being about 15 degrees, the lift coefficient is increasing. Um, this is a pretty consistent trend, and we're going to find a similar thing happening with the drag coefficient. But we're also going to take a closer look at 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 a 0 degree angle to see what exactly is happening with the flow. And right here we have the drag coefficient as it changes with the angle. Based on the research done by observing flying squirrels, the drag is usually 1/4 that of the lift. Our values do correspond to this, as that is around the ratio that we have right now. And again, we have the same direct relationship where as the angle increases, the drag also increases. So right here we have the velocity contours of the squirrel. That blue region on top represents a low velocity region, close to zero, and the bottom, that green region, is a higher velocity region. We have a greater velocity on the top than we do on the bottom. That is the kind of behavior that an airfoil would have, and it is something that is going to create lift, and it's going to correspond to an increased pressure in those same areas. We see here the same analysis being run: high pressure on the bottom, low pressure on the top, and this is going to end up pushing the squirrel upward, and this contributes to our overall lift coefficient of around 3.36. Now, the pressure differences do look small on what we're seeing, considering it's all around 101 kilopascals, but you have to remember that the squirrel itself is a pretty small object, so a difference of about 1 to 200 kilopascals, or I mean, in this case, we're looking at about, yeah, 2 to 300, 400 at the most kilopascal difference between the pressure on the bottom, pascal difference, I'm sorry, between the pressure on the bottom and the pressure on the top, is going to make a greater difference than it would on a larger body.
So the wingsuit divers that we used we took that at an average of 45 meters per second velocity, and the angle of flight we used was set to 40 degrees Celsius to actually create similar conditions to that we used for the flying squirrel. So the efficacy of the wingsuit demonstrated was compared through the lift of the diver without a suit and with a suit. And like the squirrel's anatomy, the wingsuit's purpose is to reduce fall speed to facilitate safe landing. And as you can see, the scale of the wingsuit was 1.43 meters. And here's a model of the diver without a wingsuit. And for the data that we show here, the lift coefficient, as you can see, is a lot smaller than the lift coefficient if you were to use a wingsuit.
Now we have the velocity contours for a diver with no suit. As you can see there, when we hit the middle of the diver, there's actually a low velocity region on the bottom as well as the top. That's those dark blue regions. And throughout on the sides of the diver, you do have a velocity difference, but it is nowhere near as great a velocity difference as what was seen on the squirrel. Now, of course, the numbers themselves are greater, but relative to what we're talking about for the size of it, it's not going to be significant enough to create a lift force. And this will be more directly compared to what we're going to find on the wingsuit diver. When we examine the pressure differential here, a similar thing is going to occur. You have a difference in pressure, but the difference in pressure on the bottom compared to the top is very minimal. And this is going to correspond to our very low lift coefficient of 0.06. Now, when we look at the same simulation being run on this diver, you can notice that there's a much greater velocity difference between the top and the bottom of the diver. And something to take note of is the way that the webbing of the diver's suit is deformed upwards. That is treated as a solid body by SolidWorks, whereas in reality, it'll be not really rigid. It'll be a little more flexible. And as the diver moves, it's going to an extent, move with the diver and according to the airflow. So this is a discrepancy in the simulation that is not going to be found in the real thing. And it is something to take in consideration when we're analyzing these numbers. And if you notice the way the flow goes around that part, it sort of has the effect of a spoiler and is going to affect our lift calculations because of that. Now, when we look at the pressure distribution here, we're going to notice the same thing. We have high pressure regions at the bottom, low pressure regions on top, and this is going to continue to push that skydiver upward. And as we see now, where we once had a coefficient of 0.06, we now have a lift coefficient of 2.19, which is a far greater number, and it's going to greatly facilitate the reduced fall speed of the skydiver.
So to summarize the results that Isaiah just presented, the wingsuit greatly increased the drag when compared to a regular body. And in a horizontal position, the squirrel's lift coefficient was actually 56% greater. So when comparing the same angles, the flying squirrel actually has a greater lift force than actual wingsuits. So the major difference in this design of a flying squirrel is the increased area due to the webbing stretching from the front to the back leg. Wingsuit webbing only stretches from the arm to the torso in the wingsuits, and the squirrel has a greater proportional area. So during analysis, wingsuit webbings are treated as rigid. Different wingsuit webbing materials do result in different shapes, and a wingsuit with webbing that stays relatively flat might have a greater lift coefficient. So as you can see in the table below, we listed the squirrel and the wingsuit drag and lift coefficients at different angles. So some things to consider, in order to complete our simulations on SOLIDWORKS in a reasonable time frame, we had to decrease the resolution of these models that we use in order to continually run the simulations. And the geometry of the models were fixed, but in reality, they're actually made of an elastic material. So this actually becomes relevant with the wingsuit webbing, which is treated as rigid in the simulation that you saw. So how to improve on aerodynamics? Well, both the wingsuit and the flying squirrel's anatomy have the same purpose, which is to reduce the fall speed. So the flying squirrel does this more efficiently, actually, and proposed wingsuit design features an increased area by changing the webbing size. So the webbing materials are analyzed as flat as seen in some existing wingsuits, and as shown in the contour plots that you've seen, the webbing that deforms upward actually acts as a spoiler, as Isaiah said.
So here we have the difference in area between a wingsuit diver and a squirrel. Granted, the wingsuit diver's actual area is much greater because the wingsuit is bigger, but we're talking about proportional to the size of the actual object. We can see that the squirrel has a greater area due to those bigger webbings. Here on the left, we have a wingsuit diver whose webbing stays relatively flat. There's not much deformation going on as he's falling, and you compare that to the right-hand side where there's greater deformation in those webbings. Now, what you see on the right is more akin to what we have on our model that we previously showed, and what's on the left is actually the kind of design that we're going for in the redesign. Now, granted, this does involve a new design on the webbing altogether, new materials, thicknesses, and all that. So it's not just a simple matter of changing the shape there. There's a lot of factors that have to be considered. There you can see our new design. We have the webbing being considered flat, not deforming upwards, and we have it stretching from the ankle all the way to the wrist, just like the squirrel. And there you can compare the areas and their differences. And here we have our velocity contours for the new design. Everything here is behaving as expected. We have high velocities on the bottom, low velocities on the top, and this is actually going to it contributes to our new lift coefficient of around 3.5. This is considerably greater than the 2.2 value that was found without a suit, and it is a value that is able to, well, quote unquote, compete with that of the squirrel. When we look at the same for the pressure distribution, we have low pressures in the top, high pressures in the bottom, and this is going to push our skydiver up and increase that lift as we desired. So overall, we have increasing the area of the design have the desired effect, which increased the lift coefficient. The use of the fixed webbing negated our spoiler effect, as seen in the lift coefficient, and we didn't have that phenomenon occurring in the flow contours. Now, with this design, there's a possible mobility issue because the webbing is going to be connected to the wrist and the ankle. Skydivers, after diving, are going to probably be walking around or moving to some extent, and we don't want to hinder that too much. But this requires testing to see if it's going to be a problem, and if it is, we can possibly look at removable systems to address that. And this design does have promise. It has shown to do its job, and as seen below, we have an increased lift of about 60%. And increased lift force of about 50%. So further testing can be done to put this in different circumstances and see how it's going to behave, and possibly tweak the design to see what exactly, whether it's the increased area or the change in webbing assumptions as to which one is causing a greater increase in the lift coefficient.
So to conclude, our current wingsuits are similar to the anatomy of flying squirrels, and the flying squirrel actually boasts a greater lift and therefore a greater ability to slow down compared to actual wingsuits. So as Isaiah mentioned, the webbing area is greater on the squirrel, and it can be implemented on the wingsuits as we discussed in this presentation. A new design based on findings results in an increased lift as desired, but further testing is needed. So in regards to our future work, the remainder of our work needed, we can test this new design under different flow conditions to perform further analysis and comparison. We can also refine these simulations and analysis as well. Another way, we can also run further analysis by deciding different materials to use, as well as wind tunnel testing. And we can also compare these results of the northern flying squirrel that you've seen to maybe the southern flying squirrel or flying squirrels in other areas. So the direction of the project, we can actually prototype it and 3D print it. And we can physically test this model and analyze its lift and drag, as I said, in the actual conditions. And we can test to see if the design works in an actual setting. And here are our references. And that concludes our project. Thank you.